Welcome to Vectors and Gravity. We're running through a whole series here around Unit 3 on gravity and electromagnetism. Unit 3 comes from the Queensland physics syllabus, and we'll work our way through the gravity topic of this whole section. That's where this whole video series is going to end up going. But today we're just going to concentrate initially on vectors and how they work. A few things to think about before we start. A couple of little questions there to sort of jog your memory. Before Galileo, universities taught that when a cannonball ran out of impetus, it would stop its path and fall vertically to Earth. Were they correct? Have a think about that one. I mean, the reality is, no, they weren't correct, but they weren't totally incorrect. The idea of running out of impetus doesn't exist, but an object will lose velocity until it stops and then begins to fall back to Earth. Which brings us to that next dot point there. Soldiers in war have sometimes reported that enemy bullets appear to fall vertically into their trenches. Is that possible? And as we'll see, it is possible for that sort of thing to occur. When an object is going up into the air, eventually its velocity will stop and it will start to fall back down again. All right, that's to give us a bit of an idea about where we're heading, get our mind sort of working into physics and vectors. But this slide here tells us about what it is we're going to do in this first series of videos. We're going to look at basically vector analysis and how there's two components to vectors. Solving problems. I mean, this is physics. All we ever do is solve problems in this, and it starts to look like some calculations that you'll see a bit further down, but that'll come in a future video. We're going to look at how the horizontal and vertical components of vectors start to look independent of each other. So we'll concentrate on those first few points. So specifically in this video, we're doing these things. We're going to resolve a vector into two components, add and subtract vectors, and recombine them. And you'll see that it looks a lot like some middle school mathematics. It's not that challenging. So can we resolve vectors into two dimensions and calculate the motion of an object in two dimensions? Let's just revise vectors. And no, I'm not referring to our friend over there on the right. Vector, the villain from the Despicable Me movies. In the movies, he talks about committing crimes with both direction and magnitude. Oh yeah, is the phrase that he adds with that. And essentially, it's scientifically correct because a vector has magnitude and direction. A magnitude just means an amount, a number, and a direction that it's actually directed in. So a velocity might be a vector quantity. Say I'm traveling 100 kilometers an hour from Brisbane to Sydney. That's the direction I'm traveling, and I've given you the magnitude, the 100 kilometers an hour. It's a vector quantity. When we draw vectors, just have a look on the screen there. There's several ways that we do it. Sometimes it's drawn across a actual arrow like that one. Sometimes we have this bold type text, and there's other sorts of accents we use. Probably the most common one that we tend to see is this one with the arrow on top. But look, it's just to show it's a vector. If you don't always write it, it's not the end of the world. So we've looked at vectors in the past, back in Unit 2, and we looked at the head to tail addition of them, where if I have, say, two vectors like this one here, 8 kilometers and 6 kilometers in that particular direction east, I can add them together doing the head to tail approach there, and 8 and 6 make our 14 kilometers, and east is the important bit to add, because remember, we need a direction and a magnitude. Oh yeah. Obviously the opposite down here in the second diagram is where the head to tail still adds together, but we're effectively subtracting them. That's 8 kilometers to the east, 6 kilometers to the west. The net result is 2 kilometers east. So when we look at vectors in two dimensions, which is the main thing that we'll be looking at here in Unit 3. So we're looking at a vector acting in some sort of reference direction. It's going to have that direction, which usually we're depicting as an angle, like that one there, or there's some angle here that we're putting a force here. The FA stands for force applied, so there's some angle to that one. This over here on the left-hand side, U implies our initial velocity, and we're going to look at how that's got an X component and a Y component. So let's drill that into that a bit more though. So we have an example there of like an arrow shot up at an angle, and it's got some initial velocity, and there will be a y component, which will be u in the y direction, and an x component, a u x component, like that. Now, we end up with these formulas here. So how do we do that? We have some angle that it's going at. We have an initial velocity. If you think back to your middle school maths about your trigonometric ratios, sine is opposite over hypotenuse. So sine of an angle is opposite over hypotenuse. So if I flesh that out a bit, sine of my angle theta, which is this guy down here, equals my opposite side, which is the y component of u, over my hypotenuse, which is u, my initial velocity. Now, if I rearrange that, take this guy over there, all of a sudden I have my formula here. And the same for the other component over there, sine versus cos. Be aware of the angle that's located there. Be aware that that angle at the moment is shown as like an angle to the ground, for example. Just be aware that I'm not using the other angle in the triangle that could be there. So the red boxes there are the formulas that we need to understand. The y component of our initial velocity is u sine theta, and the x component is u cos theta. Just learn those. If you ever forget them, go back to the trig ratios that you just saw me do on the previous slide. But you do need to remember them because they're not in the formula book, the data book that you get given when you do these exams. Right, let's look at an example. Here's an example of finding a machine gun. Bullets fired at, in this case, 660 meters a second at 36 degrees to the horizontal. Calculate the horizontal and vertical components. That particular machine gun there is an M60 machine gun, which was very common during the Vietnam War. Typically, it's a weapon designed to fire lots of bullets at once. Tends to be a bit of an area weapon. Not 100% accurate, but that's actually a good thing because it keeps the enemy's heads down. You can see on the right-hand side there, it's mounted on a tripod, whereas on the left-hand side there, it's only on a bipod, the two little legs that fold out. You can see them folded up there on that image on the right. They're always attached to the barrel there. Fairly heavy weapon, this thing, but most of that weight tends to be in the barrel there because you're shooting lots of ammunition through it. These things generally are useful up to sort of 600 odd meters is its mostly effective range, but the reality is when you mount it on a tripod like that and you shoot this thing up at a 45-degree angle, you tend to get the bullets going several kilometers into the distance. So how do we do this? We're going to go back to our draw ourselves a diagram and go back to those two equations we had on the previous slide. So here's our diagram. We're firing at an angle of 36 degrees. I have an initial velocity here of 660 meters per second. Break it into the y component and the x component. And it's very straightforward. Always the same maths. Put your formula down, substitute the numbers in, that's your mathematical working, and write an answer. All right, pretty straightforward. Theta is 36, so we plug that in there. Initial velocity is 660, and that is meters per second, which is our standard SI units, which we want to use. And we get an answer in meters per second. 534 meters per second is the the horizontal component of our velocity, and 388 is our vertical component. That's all you've got to do for these calculations. So recombining the vectors into a single resulting vector, we just split one vector apart into two, into an x and y component. Now we've got a y component and an x component, and we're splitting it back, combining it back into one vector. And this is just your middle school maths on Pythagoras and trigonometry. So if I know the magnitude of this one and the magnitude of this one, Pythagoras, which is right there, will tell me how big my hypotenuse is. And if we use our trig ratios again, we'll work out what the angle is that we end up with. All right, and again, think about which angle that you're asked to find and which one you're actually finding. If I'm looking within a triangle here, obviously I'm going to be finding interior angles inside the triangle there. If it asks for an angle to the vertical, that's fine. If it asks for an angle to the ground, then you'd have to subtract it from 90 degrees. Let's look at another example. Ball makes an impact with the ground with a horizontal velocity of 3 meters per second. So that would be my horizontal, ux, and a vertical velocity of 4 meters a second. That would be uy. Calculate the final velocity, just u. So I'm literally putting these two back together. In any of these scenarios, it's easy to draw a diagram. If you're not sure, it'll make the thinking a lot clearer for you. So what do I have? I have a vertical velocity going down, which is 4. I have a horizontal velocity of 3, which is effectively like that left side of my triangle, and I want to find the hypotenuse there. All right, what's that look like? Here's our diagram. So one vector of 4, one vector of 3, head to tail addition there. See, there's the head to tail just there, drawn like that, and the hypotenuse there is my resulting vector when the two are added together. Now, if you remember your middle school maths, if that side's 3, that side's 4, it's a right angle triangle. That's going to be 5. That's a Pythagorean triad. But you can work it out as well by using your Pythagoras. C squared equals A squared plus B squared. Literally plug the numbers in and work it out. One side is 3, one side is 4. That goes in for these numbers here, which we've done just there. And then when it all comes out in the wash, the answer there is 5. 5 is not your complete answer. You always need units. We're talking meters per second because it's a velocity. So the next thing to do is work out the angle, which would be that guy there. Go back to your trig ratios. Tan is opposite over adjacent. So you've got 4 and 3. So you could work it out with that. You could work it out with a sine or cos ratio if you want, but it doesn't really make any difference as long as you get to the right answer. So in this case, we're doing tan, opposite over adjacent. My opposite side's 4, my adjacent side's 3. Go back and check out the diagram if you want to look at that again. Bring your tan over the other side here, make it inverse tan, 53 degrees to the horizontal. All right, note the point down there. Depends on what the question's asking you. Is it asking you to the horizontal? That's often what we use. In some cases, the question may talk about what is the impact velocity compared to the horizontal, to the vertical. Then you just have to subtract it from 90 degrees. Here's a nice practical example of the sorts of things we've been talking about. There's a boat there traveling across a river. There's a current in the river. And effectively we end up with the boat being pushed sideways as it's still going across. What do the two vectors do? You get a resultant vector that adds together. So remember, when I want to do the magnitude, I'm dealing with Pythagoras. When I want to do the direction, I'm looking for the angle. So that would be a trigonometric ratio. Doesn't matter if we're doing this horizontal planes, vertical planes, it all still works. So remember, committing crimes with both direction and magnitude. Oh yeah. All right, what have we done? We've looked at our formulas to go resolve a vector into two components, looked at how we can add them, subtract them, looked at how we can combine them, and we can solve problems in two-dimensional motion. So we've definitely ticked off the first two on our list there. And we've started looking at the third one there, which we'll come back to and do a little bit more in the next video, where we start to deal with these equations of motion in a lot more detail. That brings us to the end today. Thanks for coming. Don't forget, do some practice questions. With any of these questions, do some practices, make sure you understand them, make sure you try some of the easier ones so you've got it straight in your head, and then skip along and do some of the harder questions towards the end of the exercise. Honestly, do yourself a favour, practice it now so you've got it in your brain. We've done 2 formulas there out of our list. We'll finish off the rest of them in the next couple of videos. So, thanks a lot for coming.